Okay, hello class. We're gonna proceed to the next chapter, which is chemical reaction equilibria. Okay, in this chapter, I simplify it and divide it into two parts, part one and part two. Okay, for the first part, we will cover on the more understanding on the concept of chemical reaction equilibria and introduction of this correlation of the Gibbs energy to the equilibrium constant. Okay, let's recall to the previous chapter that we have learned in the first half a semester. Okay, first we start with the volumetric properties of pure fluid. Okay, in evaluating the internal energy and enthalpy, we gonna evaluate that property using the volumetric properties, which we have learned about the PVT behavior. Okay, the PVT behavior can be expressed in terms of mathematical or the equation, such as by using the equation of state. We refer to the value of the pressure to determine the desired properties such as incompressibility factor, fugacity coefficient, enthalpy, entropy, and etc. Which if we have a pressure or saturation pressure higher than 15 bar, that's mean we gonna choose this method of Lee-Kessler or refer to the reference table in determining that a particular properties. And then if we obtain or the system having the saturation pressure is less than 15 bar, we gonna use a virial equation. Okay, for the virial equation, it's relate with the centric factor of that particular properties. Example, in determining the compressibility factor, so we gonna use this equation to solve if the system is not in the ideal solution. And next, we move to the thermodynamic properties. Okay, in this chapter, we develop a correlation between the first and second law of the thermodynamic, which in this chapter, we have learned more on the correlation, how to correlate that properties between both thermodynamics of law. So, we also cover on the Maxwell relation to relate between the measurable and unmeasurable properties. And we also learn about the detail on the relation about the entropy to the Gibbs energy and also the enthalpy. And the last topic covered in this chapter is the about two-phase system and the residual properties. Okay, and that's we move to the vapor-liquid equilibria. In vapor-liquid equilibria, we focus on the determining the composition at fixed temperature or pressure, or the coexisting of the phases in the system, whether we have the liquid vapor, solid vapor, or the solid liquid. But we have focused on the liquid vapor phases in the system. And in solving the problem related to the vapor liquid equilibria, we have learned about the four types of the model in this topic, which are the Roth's law. Okay, for the Roth's law, we have this PISI, P1 saturation. Okay, for the Roth's law, the liquid and also the vapor phase in ideal condition. And then we have learned about the Henry's law. Okay, for the Henry's law, in the liquid phase, the one of the component have been a diluted concentration comparing to other components. And then we introduce the activity coefficient through modified Roth's law in this model. we have this. Okay. Instead of having the ideal solution, okay, this model is implemented to the non-ideal solution, which the interaction among the molecule has been considered. And then the last model is related to the Ki value. Okay, the Ki value used the correlation of the submission of this vapor phases to the liquid phases. This value can be obtained by using the D-Pister or flash calculation. And then next is the solution thermodynamics properties. Okay, in this chapter, we have developed the foundation on the solution of the thermodynamic between the gas and also the liquid solution by introducing the properties such as chemical potential, the partial properties, the fugacity, and also the fugacity coefficient. And we have touched on the excess Gibbs energy. How can we determine these properties? And then next, we have learn about the solution thermodynamics on the application. Okay, the application that's maybe use the experimental data instead of having the theoretical data that we have learned previous chapter. Okay, for this application, okay, the first data that we expand is VLE, which the VLE is related to the activity coefficient. How can we obtain the activity coefficient from the vapor liquid equilibrium data? And then next expand to determine the excess Gibbs energy by using the modulus of Van Leeuwen equation. Okay, the next is heating mixing experiment, which how can we determine the change properties such as the enthalpy and also the molar volume in the system. Okay, next we will learn about the chemical reaction equilibria and flow sheeting. Okay, we start with the learning outcome in this chapter. Okay, in this part, okay, we have about 4 topics to be covered. First, we're gonna learn about the reaction coordinate. In this topic, you should be able to define the reaction coordinate in single and multiple reactions. And then next, we move to the application of equilibrium criteria to chemical reaction. How can you describe the equilibrium criteria to the chemical reactions, such as the criteria based on the equilibrium constant, on the effect of the temperature, and etc. And then next, we will correlate it to the standards Gibbs energy change, delta G standard, and also the equilibrium constant. And this correlation can be explained or described by using the Van Hout equation. And then for the last topic in this part, we can learn about the effect of the temperature on the equilibrium constant by investigating the effect of that temperature for that particular reaction. Okay, as the introduction, before we move to the first topic, okay, let's recall your understanding in the chemical reaction. Okay, back to the topic, chemical reaction equilibria. So first, you should be able to describe what is the definition of the equilibrium or equilibrium. Okay, equilibrium, that means there is no change on any property such as we evaluate based on the amount rate at a certain period. So that means the value is a constant throughout the time. And the example, if we consider based on the rate, okay, the forward rate and reverse rate is equally once it reaches the equilibrium. And relate to the reaction, the first place, the reactant will be higher, and then it starts to reduce until it reaches the equilibrium. At the same time, the product will be increase and reach the equilibrium by having the stagnant value at the certain period of time. This is the definition of the chemical equilibrium. Okay, the chemical equilibrium is the state of the system of the forward rate is equal to the reverse rate. And we can describe it by using the equilibrium constant. Okay, this is based on the concentration, or this is the general equation, the product over the reactant to give the equilibrium constant. By referring to the reactant, which the intention is to having the maximum conversion. That means from the reactant to the product that possibly that has possibility to having the maximum conversion. That means we're gonna have the higher yield. Okay, both equilibrium constant and conversion are function of the temperature, pressure, and composition of the reactor, which both factors are very important to obtain the higher yield in determining the correct condition, especially for the commercial chemical reaction. Okay, the equilibrium conversion are the thermodynamic criteria, and it will have this effect on the temperature, pressure, and initial composition. Okay, recall back to the understanding on the parameter relates to the temperature, pressure, and composition. Basically, it relates to the generating function, or specifically referred to the Gibbs energy. Thus, it gives us the correlation that describes to the standard enthalpy and Gibbs free energy of the reaction. Okay, let's take a look on the study done by this researcher to obtain the maximum conversion. So in general, we can say that the maximum conversion can be achieved at certain temperature, and it will start to be degrade or reduce once it reaches the maximum value. So in a principle of the chemical reaction thermodynamic, the aim is to predict this equilibrium conversion. How can we obtain the equilibrium conversion? Later, we will move to the Gibbs energy that relate to the equilibrium conversion. Okay, the first topic is the reaction coordinate. Okay, these are the general chemical reaction. We have the stoichiometric number for each species, A1, A2, 3, and so on. Okay, this is the product, and this is the reactant. Okay, the sign conversion for stoichiometric number is positive for the product and negative to the reactant. Example here, we have the methane react with water to produce carbon monoxide and hydrogen. Okay, based on the stoichiometric number, okay, first we need to balance the reaction. So the important is to balance the reaction, and then after that we can obtain the stoichiometric number for each species. Okay, let's start with the reactant. Okay, for the methane, we're gonna have -1. The V is equal to -1, and VH2 equal to -1 as well. And then we have V equal to +1 and V equal to +3. So for the product, the sign is positive, and the reactant, the sign is negative. Okay, how about with the inert species, or if the reactor, we also introduce or supply the inert species to boost up the reaction. Basically, for the inert species, the stoichiometry number is 0 because it do not involve directly to the reaction. Okay, let's take a look on the single reaction stoichiometry. Okay, for the change of the number of mole, or if we have output of the species I minus for the species I at initial, it has directly proportional to this stoichiometric number, and it represents to all the species. And for the all species, we can have another definition to describe this correlation by introduce the reaction coordinate, and by rearrange this we gonna have this difference of the number of mole equal to the stoichiometry of the species I to the difference of the reaction coordinate, and integrating this equation or this expression we gonna have this expression which the number of moles for this particular species equal to the number of moles at initial plus the number of stoichiometry times the reaction coordinate. Okay, for the single reaction, so we're gonna have one description of the reaction coordinate. Okay, later we will move to the multiple reaction. Okay, and summation all the species, it gives us the mole fraction for each species, the particular species over to the total species. So we need to obtain the total number of mole by total of this number of mole for all the species. Same goes to the number of stoichiometry by total all the number of stoichiometry for all the species. Okay, let's take a look on the example. Okay, you may try it by your own and let's compare the answer. Okay, for a system in which the following reaction occur, okay, we have the same reaction like we described in the previous example. A methane react with the water to produce carbon monoxide and the hydrogen. Assume there are present initially 2 mole of methane, 1 mole of water, 1 mole of carbon monoxide, and 4 mole of hydrogen. Determine the expression of the mole fraction expansion of the reaction coordinate. So what is the information given to us? So we have first, we have this. Okay, the first step is to extract all the information. So from this reaction, okay, ensure this reaction is balanced, and then we can obtain the number of stoichiometry. So for the methane, we have -1, water -1, carbon monoxide is a +1 and +3. Okay, the initial number of mole. So we have NCH4 represent for the initial equal to 2, and then NH2O initial equal to 1. We have NCO initial equal to 1 as well, and then the last is NH2 initial equal to 4. So how can we express? Okay, the first is to extract, and then second to express. Okay, let's take a break and then try to solve it by your own. I already extract all the information, and then we may compare the answer. So let's me write up the reaction first. So we have methane react with water, and then to produce carbon monoxide and hydrogen. So balance the equation. We have this 6, so 3. So the given first extract information. Okay, what are the information given to us is the we have the V or the number of stoichiometry -1, -1, +1, and +3. Okay, and then CH4 initial equal to 2 mole. Initial we have 1 mole, and then NCO initial we have 1 mole, NH2 initial we have 4 mole. 114. And then second is identify the equation. What's the equation to express the mole fraction and relate with the reaction coordinate? So we have yi equals to Ni initial plus Vi over total. So N naught plus V reaction coordinate. So what are the available information from this expression? So the initial mole is given. We also have the information on the stoichiometric number for each species, and then since it expressed based on the reaction coordinate, so we consider this is done as well. So we need to determine the total number of mole and also the total stoichiometric number. So N naught equal to, what is the N naught? So 2 plus 1 plus 1 plus 4. So equal to 8 mole. And then next is V. V is the minus 1 plus 1 plus 3. So we have 4 minus 2, 2. So we can, next step is, the third is to solve. Okay, how can we solve? We use this expression. So for the methane, it has Ni, so 2 plus, or since this is minus 1, K over 8 plus total is 2, and it turns to 1. 2 minus 8 plus 2. Okay, and then H2O is initial is 1 plus minus over 8 plus. So it gives us 1 minus over 8. Okay, and then the next species is carbon monoxide. So for carbon monoxide, 1, and then we have plus over 8 plus. Okay, next for the hydrogen, so we have mole is 4 mole initial plus 3 reaction coordinate and 8 plus 2. Okay, and then we already express this mole fraction to the reaction coordinate. Okay, how about for the multiple reaction stoichiometry? The multiple reaction, that means we're gonna have more than 2 independent reactions proceed simultaneously. So we're gonna introduce the same symbol of the reaction coordinate, but we insert J is represent the number of the reaction, and then the same goes to the number of stoichiometry. That's mean if we have example 2 reaction, so it turns J is reaction coordinate for 1, and then reaction coordinate for 2. Same goes to the stoichiometric number. Okay, having the same expression, so by integration, and then we can have this expression. And then by rearrange this expression, and then we can obtain the mole fraction of the species using this expression. Okay, these are the summary or the table of the stoichiometric number for the multiple reaction. Okay, example, if we have 2 reactions, so list of the species by tabulate it into the table, and then we gonna insert the value of first the value of the stoichiometric number, and then determine the initial number of mole, and then finally we can obtain the total number of mole, and by inserting all this value to this expression to obtain the mole fraction. Okay, maybe we can take a look on the example. Okay, consider a system in which the following reaction occurs. So we have two reactions. First, the product is the carbon monoxide, and the second is this carbon dioxide. Okay, where is the number 1 and 2 indicate the value of J? That's mean we have the J is referred to the number of reaction. If that present initial, okay, the initial given are for the methane and also water, determine the expression of this mole fraction as function for both reaction coordinate 1 and 2. So we have reaction coordinate 1 and reaction coordinate 2. Okay, let's solve this. Okay, maybe you can try to solve this first and compare with my answer. So the first step is to extract all the information. Okay, to extract all the information. Okay, maybe I can write up the equation first. So CH4, H2O, to produce carbon monoxide and hydrogen. So balance the equation or balance the reaction. And then the second is same reactant but producing the CO2 and hydrogen. So balance the reaction. We have 6. So 3, 4, 2, 2. So we're going to have 2, 4, 8. So we have 4. So let me check. Okay, so it balanced. And then extract the information. So we have -1, -1, +1, +3. We have -1, -2, +1, and +4. Okay, the other information given is the initial mole for both methane and water. So we have 3 to Ni and CH4 initial is equal to 2 mole equal to 3 mole. Okay, let's confirm the value. Okay, 2 and 3. Okay, we already extract the information. Second step is to find the expression. Which expression that we can use? So I equal to plus summation of the J. Okay, and not plus so we can, what is the unknown variable here? So it's already given, and then we have already have, so we need to define N0 and V. Okay, the third is to solve. Okay, to simplify this method, so we may tabulate it into the table. So the first is the reaction or J. We have only 2 reaction, 1 and 2, that give us the reaction coordinate 1 and 2. So the species are methane, water, CO, CO2, and H2. Okay, this is the V or stoichiometry for each and the total. Okay, so start with the methane. Okay, and then maybe we can insert another information is Ni. Okay, methane is 2 and water is 3. The rest is, we can neglect the rest. Okay, for the first reaction, we have -1, -1, C plus 1. Okay, consider 0 because we don't have the carbon monoxide present in the first reaction. And then we have plus 3. And the total stoichiometric number is 3, 4. Okay, -2, we have 2. Okay, how about the second reaction? -1, -2, CO is 0. We have +1 and +4. Okay, stoichiometric number is 6 or 5. -3 is 2. Okay, how to solve this? Okay, we start with the methane. So we have CH4 equal to, initial is given 2. Okay, so -1 for this, and then -2 over 5 mole plus total is 2. So 2 and also +2 for the second reaction. Okay, and then for water, so we have 3 -1 -2 over 5 plus 2. How about mole fraction for CO? So for the CO, you may refer to this line. So we have, since the initial is not given, so you may neglect it. So we have only 1 over 5 plus, and then y CO2 equal to 1 as well, but for the reaction 2 over 5 plus 2. And then the last is H2 is 3, 1 plus 4, second reaction over 5 plus 2 plus 2. Okay, this is how we express the mole fraction to the reaction coordinate in the multiple reaction. Okay, next we move to the equilibrium criteria to the chemical reaction. How can we characterize the equilibrium at the in the chemical reaction? Okay, based on the total Gibbs energy, or denotes by GT in a closed system, which we have constant temperature and pressure, by plotting the GT over the reaction coordinate. Okay, so we can add the during the irreversible process. Irreversible, that means we have only one direction of the reaction. Okay, the GT, or the total Gibbs energy, it gonna shows the minimum value. Or we have the delta GT at constant temperature and pressure equal to 0. And then at this point, we call at the equilibrium condition, which we obtain the equilibrium value for the reaction coordinate. So this is how we relate it with the equilibrium criteria. So next, we're gonna learn how can we determine the equilibrium of the reaction coordinate, because we have this minimum value of GT that give us the equilibrium state or equilibrium condition. Okay, from the correlation of the standard Gibbs energy change to the equilibrium constant. Okay, from the correlation of the standard Gibbs energy, and also introduce the composition by introduce the chemical potential into this expression. Okay, we can obtain this expression. And by replacing the delta of the number of mole to the stoichiometric number and also the delta reaction coordinate, so we have another expression. And at constant temperature and pressure, so we can have the change of Gibbs energy to the change of reaction coordinate at constant temperature and pressure. Okay, from the previous slide, we have learned that GT over the reaction coordinate. So the equilibrium can be obtained at minimum value of GT, or represent the dou GT at constant temperature and pressure equal to 0. So since the dou G, or change of the Gibbs energy over the change of the reaction coordinate, okay, we can replace this expression and it gives us 0. So the summation of the stoichiometric number to the chemical potential equal to 0. Okay, so the next step is to replace this chemical potential by introduce the fugacity, since the chemical potential is not a mathematical manipulation expression. So by replace this chemical potential, so we can have this correlation of the fugacity of solution. Okay, so the chemical potential equal to the integration constant temperature plus RT ln the fugacity in the solution, and also to relate with the fugacity in the pure species. Okay, differentiate between both, so we can have this potential equal to RT along the fugacity in the solution over fugacity of the pure species plus GI at the standard. So replace it into this expression to give us this the summation of this stoichiometry to this by replace the chemical potential. Or this expression also can rewrite based on the species. And then from this, okay, we can, okay, since it involved with the fugacity, we can have another correlation that explain the definition of the equilibrium constant. So equilibrium constant is based on the product to the reactant of the fugacity in the solution to its species. So we can have this correlation of the K equilibrium equal to the minus summation of the stoichiometric number G, or the Gibbs energy at standard over RT. So this is the important equation that we can use with it to obtain the equilibrium constant ln K equal to minus delta G, or the standard change of the Gibbs standard over RT. Okay, the change of the standard Gibbs equal to the summation of the stoichiometric number for that particular species times with the standard of the Gibbs for that particular species. So you may refer to this value, which is the change of the Gibbs standard at the reference temperature in the table of C4. We proceed with the example to obtain this Gibbs energy change at the standard. Okay, in summary, the equilibrium constant, if we have the K higher than 1, so the product favor. But if K is lower than 1, so that means we have the favor reaction. Okay, K, it can be either Kc or Kp. Kc is referred to the liquid concentration that based on the concentration of the reactant and product. And Kp is referred to the species basically in the gas condition. Okay, let's take a look on this example. Calculate the equilibrium constant at 298 Kelvin. Okay, the given reaction is nitrogen react with hydrogen to produce ammonia. And then the change of the standard Gibbs energy change is given at minus 23 kilojoule. Okay, refer to the question that we have learned, the correlation of the equilibrium constant with the standard Gibbs energy change is minus ln K equal to delta G over RT. So since the reaction in gas, so you can insert the Kp instead of K. So represent the equilibrium constant in the gas phase. So ln minus ln Kp equal to delta G standard over RT. So equal to minus 20 times 3 joule over R is 8.314 joule per mole K, and also T is 298 Kelvin. Okay, since the change of the Gibbs energy is based on the reaction, so you may insert the mole into this value that represent the change of the energy is based on the reaction. So for the Kp, okay, once you may calculate, and the answer is 10.75 the power of 3. So from this, we can have a conclusion that delta G standard is less than 1. So we can get Kp is higher than 1. So it is a product favor. Okay, let's take a look on the second example. Calculate the equilibrium constant at 500 K at delta G is 0 kilojoule. So using the same correlation, minus ln Kp equal to delta G RT. So Kp equal to 0 is 1. So at delta G standard equal to 0, so we can get the equilibrium constant equal to 1. How about the next example? Okay, we have the given temperatures is 1000 Kelvin, and then the delta G is positive. So minus ln Kp equal to delta G over RT. So equal to 23 kilojoule per, joule. So delta G standard is 23 joule per mole over R is 8.314 joule per mole K, and then the temperature is 1000 Kelvin. Okay, Kp is equal to 0.063. Okay, so from this we can conclude that the delta G is higher than 1, Kp is less than 1, or it is a reactant favor. Okay, so the equilibrium constant can provide the information whether that reaction has more reactant or product to reach the equilibrium, and it also can be correlated with the standard Gibbs energy change. From this equation, minus ln K equal to delta G at the standard over RT. So for the next is how can the temperature effect on the equilibrium constant? Okay, since the standard state temperature is related to the standard property change of the reaction, such as delta G, or the standard change of the Gibbs energy and standard change of the enthalpy will vary with the temperature. The dependence of the delta G on the temperature may be expressed using this following equation. Okay, by replace the G naught over RT to the equilibrium constant, so we're gonna have this expression and then integrate this expression to obtain this equation in determining the equilibrium constant at different conditions. So we can obtain the equilibrium constant for this particular condition by comparing between the both condition of 1 and 2. So this equation known as the Van Hoff equation. Okay, the Van Hoff equation is describe the correlation between the equilibrium constant to the Gibbs energy. Okay, the Van Hoff equation gives the effect of the temperature on equilibrium constant, thus it also affect on the equilibrium conversion. Okay, when we talk about the delta H or the delta enthalpy, we may relate it to the whether it's endothermic or exothermic depending on the sign. So if we have negative sign of the value, that means we have the exothermic. Exothermic, that's mean we have exothermic, that's mean we release heat from the system. Example, in the reaction, we have A plus B equal to C plus D. For the exothermic, we release the heat. So release heat, that's mean we're gonna have heat at the product. And then once we increase the temperature, okay, try to relate with the K equal to product over the reactant. Okay, by increasing the temperature, so we gonna reduce the value of K. So we're gonna have the decreasing of the equilibrium constant. But for the endothermic, that's mean we absorb the heat into the reaction. And then by increasing the temperature, so we're gonna increase the value of K. Because when we absorb this heat, so it gonna increase the product. Okay, let's refer to this example for more understanding about the concept. Okay, so we have the nitrogen react with the hydrogen to produce the ammonia. And these are the information given. So the first step is to extract all the info. So we have K1 equal to 4. And then the at temperature T1 is 300 degrees Celsius. So it gives 573. K. And then K2 is, we should find the K2. T2 is 600 degrees. It gives us 875 K. And then the other information is enthalpy, kilojoule per mole. So referring to this sign, so this is the exothermic. Okay, the next step is to define the expression or the equation. What is the relevant equation to be used in order for us to solve this problem? So we gonna use the correlation of this equilibrium constant to the effect on the temperature. So ln K2 over K1 minus delta H over R. And then 1 T2 1 minus T1. So we already defined this, and then the third is solve. Okay, to solve this problem, we should define what is the unknown variable. So delta H is given, is the constant value, T2, T1 is given, as well as K1. So we can solve this problem. So ln K2 over 4 minus 3, so minus 92.4 times 3 joule per mole. Okay, please make sure you standardize the unit. R is 4 joule per mole. K, and then 1 over T2 is 8.5K minus 1 over 5. Thus, we can obtain the value of K2 is 5.55 times minus 6. Let's prove the theoretical based on this value that we obtain. Okay, from this equation, so exothermic, that means we release heat from the system. So K equal to NH3 2 over N2NH2. So by increasing the temperature, so we gonna reduce the value of K because this is the reactant variable. Okay, by plotting the ln K versus 1 over T, so we can differentiate between the exothermic and endothermic. For the exothermic, we're gonna have a positive gradient. And for the endothermic, we're gonna have a negative gradient or the negative slope. Okay, previously we have learned about the equation of the minus ln K equal to delta G standard over RT. Okay, so the question is how can we obtain the change of the standard Gibbs energy? So by using the definition of the Gibbs energy at each standard, so we have G equal to H minus T as a standard. So we put the standard for each properties and then multiply with the stoichiometric number for each properties, and then it can give us the change of the standard of the Gibbs, change of the standard of enthalpy, and also change of the standard of entropy. So this is where we can start to obtain the value of standard Gibbs energy to correlate with the enthalpy and entropy. Okay, the standard heat of reaction relate to this temperature. We can using this expression, which is the standard of enthalpy equal to the standard of enthalpy at a reference temperature, or note here. Note is referred to this reference temperature, plus R by integration of the reference temperature to the desired temperature, delta Cp standard over R dt. And then for the entropy, we can have another expression that over D over T for the Cp. Okay, and then inserting this equation or the expression for both enthalpy and entropy to this equation, so we can have delta G or the change of the standard Gibbs energy equal to the change of the enthalpy at the standard and at the reference temperature minus T over T note. T notes is the standard or reference temperature. Okay, the delta S or entropy is based on the delta H minus delta G standard. Okay, why we need to replace this copy of the standard? Because in the reference table, only available data is a change of the standard enthalpy and also the Gibbs energy at reference temperature. So we can have the Cp for the enthalpy and for the entropy. So rearrange this equation and then since ln K equal to minus delta G standard over RT. So finally we can get the equilibrium constant equal to this equation to be referred in calculating the equilibrium constant based on the standard of the Gibbs and also the H. Okay, both value can be obtained from table C4. Cp is from the table C1. Okay, for each species, it has own a value of this change of the standard Gibbs energy, standard enthalpy at reference temperature, and from the table, the reference temperature is at 298 Kelvin. Okay, this table summarizes the method how can we evaluate the equilibrium constant based on the change of the enthalpy standard, change of the Gibbs standard, and also the Cp. Okay, first of all, list of the species in the table. So example, if we have nitrogen, react with hydrogen to produce the ammonia. So we have A and then 2. Okay, so this is balanced. So A is at least all the species, hydrogen and also the ammonia. And then including the number of stoichiometry. So we have -1, -3, and +2. Okay, the value of Gibbs and enthalpy you may refer at C4, table C4. I is referred to the species, and from this table C4 it gives us the value of at reference temperature, and typically usually at 298 Kelvin. And then this also are the constant based on the Cp from each species based on the A, B, C, and D. And then next to determine the change of the standard Gibbs for the reference. So the change of the standard Gibbs at the reference temperature is by multiply the stoichiometric number to the value of G that we obtain. Okay, let's test your understanding. Okay, differentiate between the endothermic and exothermic in terms of equilibrium constant and temperature. Okay, for the endothermic, we have the positive value of delta H and then minus value of delta H for exothermic. Okay, in terms of equilibrium constant and temperature. Okay, what is the difference between the exothermic and endothermic on the equilibrium constant and temperature? Example, if we increase the temperature, what happens to the equilibrium constant for the endothermic and exothermic? So you may try to recall and test your understanding by answering the reflex question. Okay. Let's take a look on this example to calculate the equilibrium constant for the vapor phase hydration of ethylene at 418 Kelvin and 593 Kelvin from the data given in Appendix C. Okay, the reaction is ethylene react with water to produce the ethanol. So the reaction is balanced. So the first step is to extract the information. Okay, the question is what is the value of equilibrium constant at temperature 418.5 Kelvin, and then second is 593.15 Kelvin. So we need to determine the K for both the temperature. Another information is the data in Appendix C. Okay, from table C1, we can obtain the value of Cp. And table C4, you can obtain the value of change of the enthalpy at standard and reference temperature, and also the standard of the Gibbs change at reference temperature as well. So the second is to define the expression. What is the relevant expression that we can use to solve this problem? So define the expression. So the minus ln K equal to delta G naught over RT. So we have value of R and also T also given. So how can we obtain the value of K and delta G standard? So delta G standard is equal to the delta G naught at reference temperature minus delta H at reference temperature over RT also at reference temperature. T naught is a reference temperature plus delta H standard over RT plus 1 over T naught T, and then we have Cp over R dt plus T naught T delta Cp the standard over R dt over T. So all this value can be obtained from the table, reference table. So how can we obtain this? Maybe we can take a look on this solution. Okay, first we start with the determine the delta Cp standard. Okay, delta or the change, that's mean we need to use this based on the product or minus reactant. So regardless any properties such as delta Cp or delta H, delta G, also you need to use this correlation based on the product minus reactant. So the first is, okay, the product is ethanol minus the reactant is ethylene and water. And then you can insert the value of A. Okay, delta A, that's mean we have A for product minus A reactant and A reactant. So same goes to the B, C, and D. So all the value may refer to the table C1 because for each species, it has own value of Cp. Okay, the next is to determine the delta H standard at reference temperature. Okay, from table C4, okay, you may refer to the species of ethylene, to the species of ethanol, ethylene, and also the water. And then it gives us the value of delta H at standard and reference temperature. Okay, the correlation is to obtain the delta H standard at reference temperature. You may use this correlation by consider the number of stoichiometry of this species. Since all the species having the stoichiometry of 1, so we have a total is 1 minus 1 minus 1, so it gives us the minus 1 to obtain the standard of the delta H at reference temperature. Same goes to the delta G. So refer to the value in table C4. So insert this value and multiply with the stoichiometric number. And then next at 418 Kelvin. So we have this delta Cp for both enthalpy and entropy. So use your scientific calculator, insert this value from reference temperature is at 298 to the desired temperature at 480. So we can get this value for both enthalpy and entropy, Cp for enthalpy and entropy. So insert all the value obtained to this equation, delta G at 418 over RT into this, because delta G over RT equal to minus ln K. So we can obtain the value of K. Okay, at 418, the K is 1.443 the power of 1. And then we can proceed to the next temperature at 593.15 Kelvin, and it gives another value. So from this, we can say that as increasing temperature, so the value of K is decreased. So it has a backward reaction, or the reactant favor, because the K is for both temperature, K is lower than 1. So in the reactor, the reactant is more favored compared to product. So this is how we conclude the effect of the temperature based on the equilibrium constant. Okay, I ended my presentation by conclude that in this part, we have learned about the correlation on the equilibrium constant with the standard of change Gibbs energy. And also we have learned about the effect of the temperature to the equilibrium constant. How can we obtain the equilibrium constant from the standard Gibbs energy and also the standard of enthalpy? So the important equation is delta G standard over RT equal to minus ln K, and the delta G standard can be obtained from the equation of delta H standard at reference and delta G standard at reference once we perform the integration of the equation. So by end of this slide, I ended my presentation. So I'll see you for the next part. Bye.